will be the conjugate Hilbert space. What is conjugate Hilbert space? Conjugate Hilbert space is the same Hilbert space as the original one, but you complex conjugate the complex numbers. Now, absolutely, it doesn't mean anything. This only means something relatively with respect to the given Hilbert space. So the canonical isomorphism between H star and H is antilinear, because I conjugated the numbers here. So I have to conjugate them in the identity. So it's anti-linear, this method. And that makes the difference, that you have this anti-linear connection which allows you for a Bell state to be defined in a natural manner. So, there is no natural isomorphism between the dual and the Hilbert space either. Just think finite dimensionally here. But there is a natural anti-linear map. And so that's what's the same thing here. Now, there is a logic to this. Maybe I shouldn't go into that because then I'm... Okay, if anybody wants to know about logic, I can talk. There is a logical thing to this. This means negation, basically. This sort of, in a logical term, this corresponds to negation. And it's like, you know that an implication can be written as not A or B. Yeah? And this is actually something like an implication, it turns out, not A to B, and that's why it makes it natural by just putting a star. There's an analogy to logic here. Because star autonomous category are actually semantics for something which is called linear logic. It's a logic in which you cannot copy and delete premises. People invented this. Linear logic is a logic in which if you cannot use your results more than twice. Why was this useful? This is useful because of resource sensitivity of, say, computational logic. In a computer, it really doesn't matter how many times you store something. And the fact that you can copy it. So to do complexity analysis, you want to make a difference between having the ability to copy and having your data represented many times, or having only represented once and being able to copy it. That's why they introduced linear logic as a logic in which you can't copy. The amazing thing about linear logic is much simpler than classical logic as a mathematical thing. Because you had nice, purely graphical proof methods, no surprise, and stuff like that. So it's a very, and now people are trying to study classical logic from the perspective of linear logic. Like, what do you have to add to logic to get classical logic, given linear logic? Because linear logic is so much simpler. And that's also where I'm now getting into looking at the classical world from the quantum world. Because the classical quantum world is much simpler. Whereas linear logic is much simpler than classical logic. People don't realize, they think classical logic is the most simple logic. No. Not at all true. It's much simpler logic than classical logic. And it turns out, the funny thing is, like, you have this linear logic which is simpler, and actually this stuff is even simpler than linear logic.
Well, you're keeping an eye on time, aren't you?
Oh, where are we now?
We're past 11:30.
Oh shit! So I should stop now, yeah?
If that's okay. Yeah.
No.
I'd rather want to go on than if I could move, you know.
Well,
what does the chairman think?
I'm now going to be an authoritarian.
Oh.
We've got other speakers.
Yeah. Well, can you
Yeah,
give
but I think we should have some compromise here then.
No, I suggest
Not
10 minutes.
compromised. I don't mind, look.
Yes. I just go in 10 minutes over.
Okay, that's fine.
Wait, like, so where are I? So, like, I'm just going to cruise to everything and then you can ask me privately about. So we saw this already, the special case of the trace. Then, so you can define stuff like, like this. So, should I want to get to the measurements now actually. Yeah, I'm going to skip this. This, like basically what I'm calculating here, this is just a calculation. You define, like if instead of Bell states, there are actually very many different entangled states.
Yeah, I was going to say, why do you single out Bell states?
So that's what I'm doing here.
Okay, you're not going to generalize.
You can define any other entangled state by taking the Bell state and just composing it at one side with isomorphism. And in Hilbert space you can do that too, and in this way you generate any biquadrate state. I do the opposite too here for the coast. And then it turns out that if I look at this configuration, I just can make a calculation, and the result is this one. So this is something you derive in this language because it's the Hilbert space satisfies this language. This is true in Hilbert space too. Now you have to read this physically. Read this physically. You start time evolves. You see something which is labeled G because it was derived using the Bell state isomorphism called G. then you meet something labeled F. Yes? The other side, you meet something labeled F and then G. This is really weird. It seems as if you violate causality here. And these are derived from the structure. Now we know that this is not true in quantum mechanics. But this mathematical fact, which is true in Hilbert space, like this is actually, you know, you have this connection between Hilbert-Schmidt maps and the tensor product. So bipartite states and linear maps. So this would be like the corresponding bipartite state through that isomorphism between Hilbert-Schmidt maps and bipartite state. And there is this seemingly a causal flow of information going on here. And that's like all the source of much of this confusing literature about teleportation, and seemingly things go back in time and are a causal. That's the mathematical fact which lies behind it. But there's nothing a causal happening here. Because you can think of this as like, you put a constraint here, you put a constraint there, and there's some special way in which constraints compose.
This is the bifunctional reality which we were talking about.
This is really compact closure.
Oh, it's compact.
This is compact closure. This is true in the Kelly categories too. This is compact closure. This is behavior of compact closure, that you've got this reverse, that there is this seeming, this is what I would call quantum information flow. It's not a physical flow, it's a logical flow. Physically, this is wrong, because this violates causality. You see, G, F, F, G is completely, because I could stop here, you could think. So it doesn't make sense. But this is logical flow, so in this picture calculus there
So
is...
there's a difference between replication and causation, that's the problem, right? That is the difference.
This, what is that? Actually, the funny thing is, like, this pulling of a rope is the same as executing two deductions, logically. Like in categories like Cartesian closure, you also have monoidal closure. Monoidal closure is actually half of this picture, logical closure. And this is like two logical deductions. It's a very... yeah, I could make this explicit, but this is the logic of the setting, and it looks very silly, but everything you get out of here, this is logical deduction. A very sophisticated, because what is typically, like I said, you've got classical logic, then you've got linear logic, in which you don't have the ability to copy and delete, and this logic additionally says that, let's put it, my conjunction equals my disjunction. Very weird. It's an extremely degenerated logic. So it's very simple, because it's degenerated, it's very simple. You can do an amazing amount of, you're allowed to basically do everything. That's quantum logic. It's like, you remember the Burke of Neumann view, quantum logic is a logic in which you basically can't do nothing, because you don't have the distributivity. We say quantum logic is a logic in which you basically are allowed to do everything. It's like much more powerful than classical logic. You're allowed to do everything. So it's a very different view. So okay, so for example, that's what I was proving now, logical closure, that you can show that this is just an implicit implementation of deduction. I'm going to not go through it. It's actually a nice proof. But, here, what I prove here, it's a pity I can't get through it, but what I'm going to do here, I'm going to show that in each such type of category, there is an analog. You remember that the whole point of Birkhoff von Neumann was getting rid of redundant global phases and stuff like that, to go projective. In this abstract setting, there is an analog to going projective, like getting rid of redundant global phases. You can actually prove a theorem which says that if you pass, so what do you do in, you know that if you pass from a cat vector to a pair of a cat and a bra, like going to the algebra, that you get rid of redundant global phases. And what you show here is that you can do this at the level of category,